This assignment begins with a classic. Actually, most of the questions in this assignment are classics. Here I have a roller coaster going through the bottom of circular motion. The roller coaster is sitting on the track on the inside of the circle. And that turns out to be important. One of the critical ideas of being successful at solving these problems is recognizing that in terms of coordinate system, when I solve circular motion problems, I always choose toward the center of circular motion to be the positive direction. So I start out with a free body diagram here for the people in the roller coaster car as it goes through the bottom of the track. So my free body diagram has the weight of the people acting downward and the normal force acting upward, exactly what you might expect. In this case, the normal force is not equal to the weight, however, because the roller coaster car is moving through the bottom of the track, and so there is an acceleration, a centripetal acceleration. Since towards the center of the circle is above the riders in the car, the normal force is a positive force in this context, and the weight is a negative force. Applying Newton's second law, the circular motion version, the sum of all the forces centripetal is equal to the mass times the speed squared divided by the radius. While the centripetal forces, or the positive normal force, minus the weight, is equal to mv squared over r. I did all of that analysis without even asking the question. And the question is, if the people feel 50% heavier as they go through the bottom of the loop, what is the speed of the car? And that's really the key to solving the problem. What you have to realize is that the normal force is the apparent weight. I think we all know that if you were on this roller coaster going through the bottom of the dip, you would feel heavier. And so all I have to do is use my equation, the normal force minus mg is equal to mv squared over r, and substitute in the normal force is equal to 1.5 times mg. Make that substitution. You'll see that the m's cancel, and then you can solve for the speed that the roller coaster car must be going through the bottom of the loop. And that really is the whole trick to solving this problem. The next problem in this assignment is one that I would have demonstrated in the classroom. I've got a little gizmo with ropes attached. I put a beaker on and swing it in a vertical circle. We discover that the beaker sits still. Well, here I have a rope to which I've tied a bucket, and in the bottom of the bucket is a rock. And as I whirl it in a vertical circle, despite the fact that the rock is not attached to the bucket, the rock does not fall out. So we want to figure out what must the speed be at the top of the loop in order for this to work. Well, as usual, I start with a good free body diagram. Here's my free body diagram for the rock. I have the normal force directed downward and the weight directed downward, mg. You're probably not surprised to see the weight directed downward, but I've drawn the normal force downward because the normal force is the force of contact between the rock and the bucket. The bottom of the bucket is above the rock, and so the bucket pushes down on the rock as it goes through the top of the circular motion. Since both the normal force and the weight in this case are directed towards the center of circular motion, they are both positive centripetal forces. So I'll write Newton's second law, circular motion form. The sum of the forces is equal to the mass times the speed squared divided by the radius. And on the left-hand side, I have the positive normal force and the positive weight. This equation is very similar to the one in the last problem, but that positive sign makes a big difference. So the normal force plus mg is equal to mv squared over r. Now, how do I solve for the speed? I don't know the normal force. Well, what we're looking for here is the critical speed at which the rock will just lose contact with the bottom of the bucket. The normal force is the force of contact. So in order to force that condition, I'm going to set the normal force equal to 0 so that mg is simply equal to mv squared over r, and then solve for the speed. You'll notice that the masses cancel. This result is such a classic that many physics students, particularly AP physics students, simply memorize this result and understand that this is the nature of motion going through the top of circular motion at the minimum possible speed. we move on to yet another very familiar problem. Here I have the roller coaster again, but instead of going through the bottom of a circular loop, it's going over the top of a loop. It's really important that you pay attention to how it's phrased in the problem, because you're going to see later on we have an example where the roller coaster is going upside down through the inside of the loop. But in this case, it's on the outside. So here I have the roller coaster like going over the top of the hill, much as the same way if you're riding in a car and the car goes over the top of the hill. So I draw a free body diagram with the normal force directed upward and the weight force directed downward. But now, since the weight force is directed towards the center of circular motion, it is a positive force, and the normal force is a negative force. So when I write the sum of the forces equal to the mass times the speed squared divided by the radius on the left-hand side, I'll write the positive weight minus the negative normal force is equal to mv squared over r. Now the problem statement says that as the people go over the top of the loop, they feel lighter. That is, their apparent weight, which we're coming to understand is equal to the normal force. Their apparent weight is less. That matches your everyday experience. You go over the top of a hill very rapidly and you feel lighter. In fact, my version of the problem, it might not be the same for everybody. I suspect maybe it is. I don't know. But my version says that the people feel 60% lighter. That is, their normal force is 60% of their weight. So in order to solve this problem, I'm simply going to set n equal to 0.6 mg. That gives me 60% of the weight. Again, the m's cancel, and I can solve for what I need to get the answer to this very classic problem. This is all becoming very familiar now as I have the roller coaster going over the top of the loop, but now on the inside of the loop. One of the more fun aspects of roller coasters. So what that does is it changes the free body diagram and makes the free body diagram for the roller coaster riders the same as the free body diagram for the rock in the bucket. The weight of the riders is certainly directed downward, and the normal force is directed downward because the roller coaster car is above the participants. Therefore, the normal force, the normal force and the weight are positive forces. So I would write the normal force plus mg is equal to mv squared over r. The key here is that the problem statement tells me that the apparent weight of the people is equal to their actual weight. So in this case, I'll set the normal force equal to mg, whereas in the previous problem I set it to 0.6 mg. Here they're telling me it's equal to mg. Getting those equations together, I can solve very easily for the unknown. The final problem in the assignment involves a centrifuge. Perhaps you're unfamiliar. Centrifuge is a laboratory device, and here's one shown right here. You see there are the little blue circular apertures on the top. You put test tubes in there, then you close the lid very tightly because it can be quite dangerous. And it spins the test tubes up to extraordinarily high velocities. And the reason why it does this is because the massive objects inside whatever you're spinning separate into layers, and then it becomes possible after you're on the centrifuge to go in with a pipette and to remove the separated material, getting just the bits you want. I remember doing this in a high school lab where we used the centrifuge to separate out superoxide dismutase from, I think it was bananas, or macerated bananas or some nonsense like that. A centrifuge spins test tubes very rapidly. To solve this, I need to first calculate the acceleration. Naturally, that acceleration is centripetal acceleration, acceleration of circular motion. So I'm going to calculate the speed squared divided by the radius. But I'm given the frequency of the thing. So for the speed, I'm going to substitute in 2 pi r, the frequency, squared, because 2 pi r times the frequency is the speed of the circular motion. You got to be careful here because the frequency is given in RPM. It needs to be converted to meters per second, pardon me. And the radius of the circular motion is given in centimeters. I need to convert that to meters. So now once I calculate that acceleration, it's going to be a remarkably large acceleration. I then want to calculate how that acceleration compares to simply dropping the test tube on the floor. So they're going to drop it from a 1 meter height, and it's going to hit the ground, and the ground's going to stop it in a very, very short time. So to calculate how much acceleration that is, the very first thing I have to do is break out some kinematics, where the speed squared is equal to the initial speed squared plus 2a delta x. I'm going to drop the test tube from rest, so I'll set the initial speed equal to 0. So the final speed squared is equal to 2g, the acceleration falling under the influence of gravity, times delta x, which is the height from which I drop the test tube. And so I calculate that speed when the test tube hits the ground is the square root of 2gh. Once I know that, I can calculate the acceleration from the definition of acceleration. The final velocity minus the initial velocity divided by the time. The time is quite short, so this acceleration is quite large, but it's not nearly as large as the kind of acceleration I get in a centrifuge.
Mm-hmm.